Okay, let's unpack this. Think about it, computers, not just calculating, but actually creating, writing text that sounds completely human, making art, composing music. Felt like science fiction not long ago.
It really did. That ability to generate something genuinely new, coherent, it seemed like a purely human skill.
But, well, it's here now. And that's why today we're doing a deep dive into generative AI. We've got this really helpful article, a simple guide to generative AI, and our goal is to break it down for you, figure out what generative AI is, where it popped up from, how it works under the hood, and, what it might mean for the future, sort of cutting through the noise.
Absolutely. And, to really get generative AI, it helps to just quickly set the stage. You're probably familiar with artificial intelligence, right? Building machines that do tasks needing, well, human-like intelligence.
Right, like understanding speech, recognizing faces, maybe making decisions. And machine learning, that's the part where computers learn from data instead of needing every single rule spelled out.
Exactly. ML is a core part of AI. Instead of hard-coding rules, you show the machine loads of examples, say pictures labeled cat or not cat, and it figures out the patterns itself. This learning from data idea is fundamental to modern AI, and it's absolutely crucial for generative AI. It lets these models learn the really complex patterns in language, images, sound, whatever, from just massive amounts of data.
Okay, so we have AI as the big picture, ML as the learning method. Where does generative AI fit in specifically?
So generative AI is all about creating new stuff that looks or sounds like the data it learned from, but isn't just a copy. Think writing a totally new email that reads like a person wrote it, or creating an image in Van Gogh's style based on your description.
And that's different from, say, my spam filter.
Totally different. Your spam filter is what we call discriminative. It learns to tell things apart, spam versus not spam. It classifies, it judges.
Ah, I see. But generative models, they're creators.
Pretty much. They learn the underlying structure, the essence of the data, so well that they can produce brand new examples that fit that structure. They don't just classify, they synthesize.
Okay, that makes sense.
And that's why it's exciting. It opens doors for automating creative work, writing, design, music, and also for things like generating synthetic data. Like if you need more examples of rare medical scans to train another AI, you could potentially generate realistic-looking fake ones.
Fascinating. So this didn't just happen overnight. What's the backstory here?
No, definitely not overnight. There were earlier statistical methods like enneagrams or hidden Markov models that had some basic generative abilities. But things really started heating up with neural networks maybe around 2010 to 2014. You had autoencoders learning to compress and reconstruct data.
Okay.
And then variational autoencoders, VAEs, which added a clever twist. They made that compressed representation probabilistic, sort of fuzzy, which turned out to be much better for generating smooth variations and new examples.
So VAEs were good for images, maybe cleaning up noisy data, but the guide mentions a real game changer around 2014.
Ah, yes. GANs, generative adversarial networks. Introduced by Ian Goodfellow, the big idea was competition, setting up two neural networks to fight it out.
Right, the generator making fakes and the discriminator trying to spot them.
Exactly. The generator takes random noise and tries to turn it into something that looks like the real data, say, a realistic face. The discriminator sees both real faces and the generator's fakes, and its job is to get better at telling which is which.
Well, they're constantly trying to outsmart each other.
Precisely. The generator learns to make better fakes to fool the discriminator, and the discriminator gets better at spotting fakes, which forces the generator to improve even more. It's this adversarial cycle.
And that leads to really realistic results.
Incredibly realistic, especially for images. GANs were a huge leak. Think deepfakes, realistic artwork generation. Though they can be notoriously tricky to train well, very unstable sometimes.
Okay, so VAEs, then GANs, and then the guide points to 2017 as another pivotal moment.
Yes, 2017. The paper, Attention is All You Need. This introduced the transformer architecture and the key mechanism inside, self-attention.
Self-attention, allowing every part of the input, like every word, to look at every other part.
Exactly. Before transformers, models like RNNs processed sequences step by step, which made it hard to connect words far apart. Transformers, with self-attention, can weigh the importance of all other words simultaneously when processing a single word. Plus, they could be parallelized much more easily.
Which means faster training.
Much faster training on modern hardware, and crucially, much better handling of long-range dependencies, understanding context across long stretches of text. That was huge for language.
And this is the foundation for models like GPT.
Yep. GPT stands for Generative pre-trained transformer. These models are trained on vast amounts of text, basically learning to predict the next word in a sequence. That simple objective, scaled up for the transformer architecture and massive data, leads to models that can generate incredibly coherent and human-like text. You also have models like BERT, T5, PaulM, Llama, all building on these transformer concepts.
And it's not just text anymore, is it?
Not at all. The pace is incredible. We're seeing powerful multimodal models now, systems that work with text and images or audio. Think DAA, stable diffusion, Midjourney, generating images from text prompts, CLIP, understanding the relationship between images and text, even early steps in video and sophisticated audio generation.
Wow, okay, so that's the journey. But let's get into the mechanics a bit. How does something like self-attention actually work? Or how does a GAN learn?
Okay, well, starting really basic, it's all built in deep learning. You have these networks of artificial neurons, right? Simple processing units. They're arranged in layers.
Deep meaning many layers.
Exactly. Many layers. In image recognition, early layers might detect edges, middle layers shapes, and deep layers complex objects. Learning happens by adjusting the connections, the weights, between these neurons
How does that adjustment happen?
through training. You feed data in, that's the forward pass. The network makes a prediction. You calculate how wrong it was using a loss function. Then comes backpropagation, figuring out how much each weight contributed to the error and nudging it in the right direction to reduce that error. Optimizers are algorithms that guide this nudging process smartly.
Okay, standard deep learning. Now map that to transformers and self-attention. You mentioned query, key, and value.
Right. So for each token, think of a word or part of a word. The transformer creates three vectors: a query, a key, and a value. The query is like the token asking, what should I pay attention to? The key is like the token announcing, here's what about. The value is the actual information the token holds.
And the attention comes from comparing queries and keys.
Yes. Each token's query vector is compared to every other token's key vector. This comparison gives a score: how relevant is token B to token A? These scores are then normalized, using softmax, to become weights. The final output representation for token A is a weighted sum of all the value vectors, weighted by those attention scores.
So it learns which other words are most important for understanding this word's context.
Precisely. And multi-head attention just means doing this whole query key value process multiple times in parallel with different learned transformations, allowing the model to focus on different kinds of relationships simultaneously, maybe syntax in one head, semantics in another.
Makes sense. But attention doesn't know word order, right?
Good point. That's where positional encoding comes in. It's an extra signal added to each token's input that tells the model its position in the sequence, often using sine and cosine functions.
Okay, so when GPT writes text, how does it use all this?
GPT models typically work autoregressively. That means they generate text one token at a time. You give it a prompt. It uses self-attention, specifically mass self-attention, so it can't cheat by looking ahead, to consider the prompt and any tokens it's already generated. And then it predicts the single most likely next token.
And then it adds that token and repeats the process.
Exactly. Predict token, add to sequence, predict next token, add a sequence, and so on, until it hits a stop signal or a length limit.
Got it. And quickly, back to VAEs and GANs. How do they actually generate the new stuff after training?
For VAE, the encoder learns to map input data into a smooth, latent space described by probability distributions. To generate something new, you just pick a random point from a simple distribution, like standard Gaussian, in that latent space and run it through the trained decoder network. Because the space is smooth, points near each other decode into similar, plausible outputs.
So you sample from the learned possibility space and jam.
With GANs, once training is done, you basically just use the generator network. You feed it a vector of random noise, and because it's learned during the adversarial game how to transform noise into realistic data, it outputs a new sample, a new image, or whatever it was trained on. The discriminator is mostly just needed for the training phase.
Okay, so these models are incredibly powerful. But how do we, as users, actually steer them? Tell them what we want.
That's the crucial skill of prompt engineering. Since retraining these huge models isn't feasible for most people, you interact with them by carefully designing the input text, the prompt.
It's like figuring out the magic words.
Kind of, yeah. The guide mentions different strategies. Zero shot is just giving the instruction directly. Summarize this article. Few shot is giving the instruction plus a few examples of what you want, like showing it English. Hello Hindi de noyate, a couple of times before asking it to translate a new sentence.
And chain of thought.
That's asking the model to think step by step, basically showing its reasoning process. It often helps it tackle more complex problems more accurately.
What makes a good prompt?
Clarity is key. Be specific, provide context. Good examples help a lot in few shot. Using clear formatting can guide the model. And you can often tweak parameters like temperature higher means more random, creative output, lower means more focused, predictable output, and max tokens to control the length. It's really about learning how to communicate effectively with the AI.
And this prompting is what enables all those applications we hear about.
It's a huge part of it, yes. For text generation, think chatbots getting smarter, customer service bots handling complex queries, maybe even in multiple languages like the Hindi example mentioned, or generating marketing copy blog posts, social media updates saving tons of time.
Summarizing long reports or emails, too, that's useful.
Definitely. Translation gets better, more nuanced, even personalized learning. Generating explanations tailored to a specific level, like explaining physics to a child in simple terms.
And encoding.
Big impact there. Tools like GitHub Copilot use generative models to suggest code, complete functions, even write boilerplate code based on comments. It speeds things up, potentially reduces bugs.
Wow. You can even ask it in plain English to write a database query.
Yeah, translating natural language to SQL or other query languages is a growing application.
Then there's the creative explosion, images, video, audio.
Absolutely. Text-to-image models like DALL-E, Stable Diffusion, Midjourney are transforming art and design. You just describe what you want. We're also seeing AI used for image editing, removing objects, changing backgrounds based on prompts.
Video is still early days, you said.
Relatively early, but improving fast. Generating short clips from text is becoming possible. Audio is interesting too, generating music, different styles, even singing voices, and cloning voices for dubbing or audiobooks.
And what about this synthetic data idea again? Why is that so important?
Because sometimes real-world data is really hard or expensive to get, or it's privacy sensitive. Think medical records or footage for self-driving cars in rare conditions.
So you generate fake but realistic data.
Exactly. You can train a generative model on the real data you do have, and then use it to generate lots more artificial examples. This synthetic data can then be used to train other AI models, helping them learn better, handle edge cases, and avoid privacy pitfalls. It's used in healthcare, autonomous vehicles, speech recognition for different accents, lots of areas.
Okay, so it sounds amazing, but the guide also mentioned challenges. It's not perfect.
Far from it. Hallucinations are a big one. Models can just make things up, state false facts with complete confidence. You absolutely need to fact-check important outputs.
That seems critical.
It is. Then there's the sheer computational cost. Training these enormous models takes massive amounts of energy and specialized hardware. Running them efficiently, inference is also a challenge, especially for real-time use. Cost and latency are big factors for businesses.
How are people tackling that?
Lots of ways. Developing smaller, more efficient models, using specialized chips like GPUs and TPUs. Cloud platforms offering optimized services. Techniques to shrink models after training, like quantization.
What about bias? We hear a lot about AI bias.
Huge issue. Models learn from the data they're trained on, and if that data reflects societal biases, sexism, racism, the model will likely replicate and even amplify them. Careful data curation, filtering, bias detection tools, and human oversight are crucial, but it's an ongoing struggle.
And data privacy, especially with sensitive info.
Also critical. Compliance with regulations like GDPR or IPACIA is essential. Techniques like federated learning, where the model trains on decentralized data without the raw data leaving the user's device, can help. But it's complex.
Explainability is another one, right? These things being black boxes.
Often, yes. It can be very hard to understand why a model made a particular decision or generated a specific output. That lack of transparency is a problem, especially in high-stakes fields like medicine or finance, where you need accountability.
Plus the broader ethical stuff, deepfakes, misinformation, potential job impacts.
All major concerns. Security risks, too, generating more convincing phishing emails, for example. These are societal challenges we need to grapple with as the technology advances.
So looking forward, what are the big research directions? Where is this heading?
Well, one trend is definitely towards bigger models, but also, paradoxically, more efficient models. Finding ways to get more capability with less compute, maybe through architectural innovations or techniques like pruning away unnecessary parts of the network.
And more multimodality.
For sure, models that fluidly integrate text, images, audio, video, maybe even other sensor data. Think having a conversation with an AI that can see what you're seeing and understand your environment.
What about making them safer and more aligned with what we want?
That's a huge focus. alignment research,
Mhm.
using techniques like reinforcement learning from human feedback, RLHF, to better train models to be helpful, honest, and harmless, developing safer ways for them to explore and learn.
And maybe learning continuously.
Yeah, continual learning is a goal, enabling models to keep learning from new data streams over time without catastrophically forgetting past knowledge or becoming unstable. It's tricky.
Will we see more specialized AIs?
Very likely. While large general models are powerful, we'll probably see more models fine-tuned or built specifically for domains like law, medicine, finance, scientific discovery, and hopefully better tools for explainability to peek inside that black
And
box.
making it all more accessible.
Definitely. The open source movement is strong here. Platforms like Hugging Face, making models and tools widely available, fuels innovation and allows more people to experiment and build.
Okay, so for listeners who are maybe intrigued, maybe a little intimidated, but want to learn more or even get their hands dirty, what's the advice?
Don't be intimidated. Break it down. The guide suggests start with the basics. Learn some Python if you haven't already. Get a grounding in core machine learning concepts, classification, regression, how training works. Andrew Ng's courses are famously good starting points.
Then move into deep learning.
Yeah, understand neural networks, backpropagation, then pick a framework like PyTorch, often seen as a bit more beginner-friendly, or TensorFlow, and try building something simple.
And for the generative stuff specifically.
Learn about transformers. Understand self-attention. The Hugging Face library is an amazing resource. Here they have tutorials, pre-trained models you can easily load and play with.
So experiment.
Absolutely. That's the best way. Try using a pre-trained model like GPT-2 or run a Stable Diffusion notebook online to generate images. Maybe try a small project. Build a simple chatbot for FAQs, try style transfer on images, generate some simple synthetic data.
And keep learning because it moves so fast.
Exactly. Follow key researchers and labs on social media. Read blogs from places like OpenAI or Hugging Face. Subscribe to newsletters like The Batch or Import AI. It's a constant learning process.
Right. So wrapping this up, we've seen generative AI isn't magic. It's built on these layers of machine learning, deep learning, especially architectures like the transformer. It's math, data, and clever engineering.
And while complex under the hood, the core ideas like attention, adversarial training, prompt engineering are graspable. The tools are becoming more accessible all the time.
It feels like understanding and being able to use these tools is becoming increasingly important, almost a new kind of literacy across so many fields.
It really does. The potential for creativity, for problem solving, for just doing things differently is immense.
So the final thought for you listening, with these powerful tools getting easier to access and understand, what interesting problem could you tackle? Or what creative idea could you explore using generative AI? The landscape is wide open and, well, the future is kind of yours to generate.